Today, I yeah. Oh, mhm. This is the distribution of rooftop albedo we made estimated from Sentinel-2. So resolution Sentinel-2 is 10 meters. Yeah, while it is quite high, but still, pixel observing the edge of the building involves not only pure building footprint but also other elements like the road or street trees. In our database, we tried to reduce such noise by using the AI. Today's my talk is about why and how to make this database. Our database is made for urban canopy model in weather simulation. Urban canopy model is one category of land surface model which parameterize heat, vapor, and momentum exchange between land surface and its above atmosphere. And rooftop albedo is one important parameter in urban canopy model because it controls the absorption of solar energy to the cities. In fact, there are many numerical studies looking at the climate impact of changing rooftop albedo to high reflectivity ones, so-called cool. And they reported about 0.5 to 3 Kelvin reduction near surface temperatures. Yeah, however, because of our limited knowledge of actual rooftop albedo values, yeah, frankly speaking, their findings might not be trustworthy. So that is the driving force for us to make a database over the world. Although using satellite data is only solution for database over a wide area, open satellite data, including Sentinel-2, doesn't have resolution enough to capture pure building footprint. So our approach is applying the super resolution algorithm, which is a technique to increase the image resolution, yeah, like this with AI. Applying the super resolution algorithm to the open satellite data could yield nicely sharpened image with visible building outline, I hope. So we made a model based on EEGAN, first proposed by Zhang et al. The network of the model goes like this, which has a generator network and a discriminator network. Generator network consists of increasing resolution block and edge enhancing block. Output image of a generator network then judged by discriminator network with the ground truth images. In training, this process is repeated until the discriminator network satisfies the performance of the generator network. In our model, input is a low-resolution albedo estimated from Sentinel-2, whose resolution is 10 meters, and ground truth is albedo estimated from a commercial satellite, Worldview 3, with 1.25 meter resolution. Although original EGAN was made to increase the resolution 4 times, it is not sufficient for our objective, so we upgraded the model for 8-fold increase in resolution. Hereafter, I call our model XEGAN, meaning extended EGAN. Sorry for your And training and validation was done for a commercial district over part of Tokyo with 5 times 5 square kilometers, in which coverage ratio for building 37%, for road 21%, and for water less than 1%. And we applied the cross-validation technique to validate our model, in which a target area divided into 4 regions with equal size, and one of them is used for validation and other for use training. So the cross-validation was applied 4 times by shuffling the training and validation data like this. Okay. Here the flow of making the database. In pre-process, first we need to calculate the albedo from each narrowband reflectivity of Sentinel-2, and we applied some simple solar altitude correction I show you later. After training and validation of the model, the main process first predicting super resolution albedo image. Second, averaging them for each individual building to extract the rooftop albedos. Finally, composite averaging with other albedo image taken at different dates to increase the accuracy. I'm going to show you these four results first. First one is solar altitude correction. This is a time series chart of spatially averaged albedo over the target area. Please look at the green and blue plot. Green plot are from the Sentinel-2, taken when solar altitude angle was more than and equal to 50 degrees, and blue one at below 50 degrees. You can see clear dependency, you can see clear seasonal trend as well as the certain bias when we compare ground truth shown in orange line. This discrepancy possibly comes from the shadowing effect of a building morphology or three canyons. So we first formulate a single regression formula to eliminate these discrepancies. So regression formula was established between ground truth image and these green data. Red one shows the result of the solar altitude correction. So now we have the consistent albedo values regardless of the data of the and date of the data acquisition. Here, I show you a sample of the super resolution image with our model XE as well as the conventional two interpolation method nearest neighbor and by cubic shows as your benchmark. Top three panels show without solar altitude correction, and bottom three with solar altitude correction. Here the prefix modified indicates the with solar altitude correction. Please remember that. And images from our model XE and modified EGAN look similar with ground truth, although nearest neighbor and bicubic look fuzzy in outline, as well as there is a very apparent biases without solar corrections. With these images and building footprint data, we extract the pixel within the building and average them for making the rooftop albedo. And this is the rooftop albedo between ground truth and predicted one in vertical lines. The color indicates the frequency of the data. Again, our model XE1 outperformed nearest neighbor and bicubic with higher linearity and determination coefficient. However, there are some dispersion even in XE1, so we try to reduce this error by composite averaging. Composite averaging is the averaging operation with other albedo data taken with different date. So this panel with vertical axis of RMSE indicates so error decrease with the number of ensemble members. Okay. Thanks to our solar altitude correction, so we have consistent albedo value, so we can do composite averaging without spreading the uncertain range of the uncertainty. Another advantage of composite averaging is reducing the region of data missing, maybe coming from the cloud cover or etc. So this graph shows coverage ratio become almost unity with four ensemble members. So composite averaging at least four members would be preferable both in terms of accuracy and filling missing data. To this slide, I show you the accuracy of a prediction model in terms of the each building basis, but our objective is to make a database for weather simulation. So data for individual building are overperformance. So this is relation between error and spatial averaging resolution. In 1 kilometer resolution, after composite averaging with 4 members, our model shown in green plot, error decreased to 0.1. So it is reasonable accuracy, I think. And this is a distributed rooftop albedo in our database in 1 kilometer. So the value ranges from 0.16 to 0.24 mostly. It's not homogeneous, it's not uniform at all. It varies between cities to cities. So you may concern about the uncertainty or you may concern about the acceptable accuracy. So we looked at the uncertainty associated with instrumentation. So there are several methods for albedo measurement. About that point, you can check these my co-author's presentation. Maybe one of them already finished, but you can access the user's presentation. Okay, our methodology requires not only sentinels but also building footprint data. But no worry. So nowadays, several open building data are available, such as Open City Model or OpenStreetMap. So expanding the database to over the outside Japan is possible. Now we are making the USA's building rooftop database. We are making the rooftop albedo database over the USA. Okay, I'll skip this. So this is a summary of my presentation. I won't read out because I consumed a lot of time, but yeah. Our research is financially supported by this project, and I will be happy to answer if you have any questions. Please don't hesitate to contact me anytime, anywhere, even during the conference. So thank you for your attention.
Thank you, Dr. Nakayoshi. Do we have any questions?
This is really useful work. I was wondering, I'm assuming you can already do something similar for road albedo. Do you have, and do you have any thoughts for wall albedo?
Yeah. Our primary interest is rooftop albedo because it is very important. So road albedo, if road albedo is high, then reflective solar radiation will be absorbed by wall or some building. But yeah, rooftop albedo was not such. Anyway, our primary interest is rooftop albedo, but possibly we could extract the rooftop roadside albedo with these algorithms, possibly, or perhaps, or we hope so. Or
are most rooftops in Japan there got angles on them and all sorts.
Yeah.
So does that not complicate your correction? Because that means even in the same roof you're going to get lots of different obvious albedos based upon reflectors.
Yeah, angle dependency of albedo was not investigated yet. Yeah, it's very important factor. But nowadays, in current situation, we assume the flat roof.
All right. Any more questions? No? Well, thank you very much. Next, I'll call up Harsh Kamath. He is presenting Globus, the Global Building Heights for Urban Study.